So this is the shape of a converging lens. You can see at the center of the lens is a point which we call optical center. What do we call this? Optical center. So optical center is basically the exact center of the lens. Optical center is the exact center of the lens. अच्छा जी, उसके बाद अगर मैं आगे बढ़ूँ, so this is a horizontal line passing through the lens. A horizontal line passing through the lens. We call this the principal axis. We call this the principal axis, right? And for every lens, this is a biconvex lens. Bi means two. It means it's curved on both sides. Bi means two. It's curved on both sides, so it would have two focal lengths. It would have two focal lengths, or in other words, two focal points. What is a focal point? We'll just move ahead and we'll discuss that. But before I move on to discussion of focal points, I would introduce some more terms here. This line, this vertical line, the y-axis, which passes right through the focal point, is called focal plane. It's called as focal plane. So you have two focal planes again, the two orange lines, yes. Then you have this distance from the optical center, to the focal point. Optical center to the focal point, known as focal length. The distance from the optical center to the focal point is known as focal length, right? Any problem, any confusion? Alright, I have also identified these terms one by one. So optical center is what? It's the exact center of the lens. Optical center is the exact center of the lens. Then what is principal axis? Principal axis is basically the horizontal line through the center of the lens. Then what is the focal point? Focal point is point on principal axis. Point on principal axis. What is focal point? A point on principal axis. A point on principal axis where all light rays that are coming parallel to principal axis, meet. Parallel to principal axis meet, or they converge after striking the lens. What do I mean by this? Let's say if you have a ray coming here parallel to the lens, it strikes the lens, and after passing the lens, it will pass where? Through the focal point. A light ray coming parallel to the principal axis but just below it, when it strikes the lens here, it will go and it will pass through the focal point, right? So focal point is a point where light rays coming parallel to the lens will merge at the point where light rays coming parallel to the lens will merge at, right? And they will merge after they pass through the lens. Then the vertical line, the y-axis, is the line through the focal point. I already told you that. And the focal length is basically distance between the focal point and the optical center. Alright, so I'll move on and we are going to discuss some more stuff. So we are going to talk about ray diagrams. And for ray diagrams, we have certain rules. Rule number one is that if a light ray coming and striking the lens at the center, that is optical center, then that light ray will pass through undeviated. It would not change its direction. It would go straight through, right? So what does that mean? Just look here. So this line, I'll just make it. This line, which was coming parallel to the principal axis, after it strikes the lens, it will pass through focal point. So any line coming parallel to principal axis, will pass through the focal point after striking the lens. And any line that strikes the lens at the optical center will go undeviated. इसको ढक दो थोड़ी देर बाद, ठीक है? Will go undeviated. Got it? Undeflected. Alright, so moving on. The first rule is missed over here. I'll just make it again. Okay, Look here. This is the light ray coming right, striking at the optical center, and it will go undeviated. Right? A light ray striking at the center will go undeviated. A light ray striking at the center will go undeviated. A light ray striking at the center will go undeviated. Right? Got it? Any light ray coming parallel to principal axis will pass through the focal point. Right? It will pass through the focal point. Got it? Coming parallel to the principal axis, it will pass through the focal point. Coming parallel to principal axis will pass through the focal point. Coming parallel to the principal axis will pass through the focal point. Right? And the third rule, which I do not consider the third rule, actually it's just a reverse of the second rule. That is, if a light ray is coming parallel to, if a light ray that's coming and striking the lens after passing the focal point, this light ray, as it emerges from the lens, will become parallel. Emerges from the lens will become parallel to the principal axis. Got it? So isn't it a reverse of this one, that a light ray coming parallel to principal axis will pass through focal point? So a light ray coming through focal point, then striking the lens, will go and become parallel. Yes. So these were the three rules. And then chalo, this is going next. All right. Okay. So see, these light rays coming parallel to the lens will meet at the focal point. These light rays coming parallel but not coming parallel to the principal axis, they will meet somewhere on the focal point. Again, these light rays coming parallel together but not parallel to the principal axis will meet at some point there. Right? So they will meet on focal plane. Got it? Any problem? Parallel will meet at focal point. Parallel to principal axis, they will meet at focal point. Meet at focal point. But if they are parallel together, not parallel to the principal axis, they will not meet at focal point. They will meet somewhere on the focal line. Right? Focal plane. Got it? Okay. Moving further. This is a diverging lens. Again, it's biconcave lens. It's curved inwards from both the sides. Right? So it's biconcave lens. This is the optical center. Again, the same rule goes for this one, that if a light ray is coming parallel to principal axis, just if this is the light ray coming parallel to principal axis, now it will deviate. It will not converge. It will diverge. So it will go there. It will diverge like this. But you would make its path back. This is the point where it will pass through the focal point. If there's another ray coming here parallel to the principal axis, it will diverge. Right? But when you trace back, it should pass through the focal point. A light ray coming parallel to the principal axis will diverge. But when you follow back, it should pass through the focal point. A light ray coming parallel to principal axis, it will diverge. But when you follow it back, it should pass through the focal point. Right? So this is diverging lens. And this image, you know that the light rays actually are going this way. Are there any light rays that are coming back? No. You have just virtually extrapolated the line. You have just extended the line. Is it? You have extended the line. So you have made virtual line. There is no line existing. So this will make a virtual image. Right? And the virtual image will always be smaller than the actual object. I hope that's understood. Alright. Moving further. So this is one case. A light ray coming parallel and a light ray passing through the focal point. Focal point wali, it goes undeviated. right? And here it is. The light ray coming parallel will meet at focal point, once again, right? And you make the virtual ray as dotted. You make the virtual ray as dotted, is it? Right? So this is where your image is going to form. This is the point where the image is going to form. This is the point where the actual ray and the virtual ray meet. Your object was placed over here. There were two rays coming from this object. How many? Two rays. One parallel to the principal axis. Parallel go diverges, and you just trace it back. You just trace it back through the focal point. This other ray coming from this object passes through the optical center undeviated, right? So you see that the actual ray and the virtual ray are meeting at this point. This is the image of this arrow. This is the image of this arrow. Is this image smaller? So the image is diminished. If the image is smaller, the image is diminished. Got it? Alright, moving further. So this is the virtual ray. I have just talked about this. This is the image. These are more light rays. Got it? Any confusion? Any problem? So going further, there are some cases. There is only this one case for diverging lens. Diverging lens का सिर्फ ये case है. But for converging lens, you have a couple of cases, at least 6 of them. See, this is a converging lens. These are focal points on it, right? Now we have distance to be measured in meters, centimeters, kilometers, hours, and so on. But when you measure the length of a lens, you measure it in terms of focal length. So this f is at a distance of 1 focal length. This f is at a distance of 1 focal length. This 2f is a distance of 2 focal length. This 2f is a distance of 2 focal length. At this point in time, you have placed this object somewhere very far away from optical center. Even more than 2f. The length is more than 2 focal lengths. The length is more than 2 focal lengths, right? So what do you do? What you will do? You need 2 rays always. Number 1, ray passing straight through the origin. Ray number 1 passing straight through the origin. Ray number 2 coming from the top of the object, meeting the lens, coming parallel to the principal axis, and then passing through focal point. And this is the point where the 2 rays meet. So this is the image. This is the image of the object. The arrow was up there. The arrow is down here now. The arrow was this size. The arrow is now at a smaller size. So basically, the image is diminished. The image is smaller. Got it? Image is smaller. One more thing you can see is, are these rays actually meeting, or you have just extrapolated the lines? They are actually meeting. They are really meeting. So this is a real image. This is a real image. This is a real image. This is an inverted image. Right? Is it upside down? It's real, but it's inverted. It's real, but it is diminished. It is. Got it? Any problem? Any confusion? Can you tell me any practical example where this type of lens is used, where the image is smaller than the object? Shabash. Excellent. One natural example. Eyes. Excellent. So you use this type of formation in eyesights and in cameras. So image is real, diminished, and inverted, right? And a practical application is camera and eyesight. Got it? Any problem? Any confusion? Another case. Case number 2. The light ray passed. This is the lens. Now I bring the object closer together. Previously it was some distance far away than 2f, 2 focal lengths, right? At this point in time, it's exactly at 2f. It is exactly at 2f. So when it is exactly at 2f, I'll follow the same rule. One ray goes straight through optical center. One ray goes straight through optical center. This ray will go undeviated, undeflected. It will not change the direction. The second ray comes this way, parallel to the principal axis. As it passes the lens, it will pass where? it will pass from the focal point. This was the rule. It will pass from the focal point. So this is the point where you see, that the image is being formed. Now I'll just make the image and let's see, is the image the same size? Image is the same size. Excellent. Is the image inverted? It's inverted. Are the rays actually meeting? They are meeting. So it's a real image, it's inverted image, it's the same size. Can you think of some practical application where the image is the same size as the object? Come on. We have this application present right in front of the entrance door of our center. When you cross the mirror, it's to the left of the mirror, left of the door. Photocopier. Just go see there. Photocopier. This is used in photocopier. The document size you get printed is the same as the original document. So the image is the same size. Image is the same size. Got it? It's used in photocopier. Any problem? Any confusion so far? Then I bring the object further closer together. What you would find over here, the closer you bring the object, the greater the image is, isn't it? So now you keep the object between focal F and 2F, right? F and 2F. And you follow the same rule. One ray passes straight through. The second ray becomes parallel to the principal axis and then passes through focal point. This is where they meet. Do they actually meet? So it's a real image. Now this is inverted image as well. Is it the same size? It's enlarged, magnified, right? So the image is inverted. The image is larger or magnified and real. Got it? Any problem? Any confusion? Can you think of any practical application for this type of lens? Magnifying glass? No. It's not a real image. Projector, yes. Projector or photographic enlarger. Got it? Any problem? Any confusion? Alright. This is the second last case. Now I bring the object even further. I keep the object at 2F. At F, sorry. Right? I obey the same rule. One ray passes straight through the origin and that goes undeviated. The second ray comes parallel to the principal axis and then it passes through focal point. What do you see? What has happened? The two light rays have become parallel. Right? So that means the image is formed at infinity, at unknown distance. So if it's not known, that means it's not a real image. So the image is virtual. Because the rays do not meet. The image is virtual. And if we look at the trend, what has happened? The image has began to increase in size. So where is it used? It's used in spotlights. Where is it used? So it's virtual, it's enlarged, and it will be upright. Up till now, all the images were inverted. But now it's upright. Now it is upright. Got it? The last case of this is this. And let's say I keep the object inside F. That means the object is placed between optical center and focal length. So what will happen? I'll obey the same rule. The first ray goes undeviated, right? So the second ray comes parallel to the principal axis and then passes through F. So again you see that they are spreading out. They are not meeting. So you trace them back, you would find them over here. But you have traced them virtually. They are not really lying there, isn't it? So that means this image is not real once again. This is a virtual image again. This is magnified again, and this is upright again, right? So the image would be magnified, right? The image would be magnified, the image would be upright, and the image would be virtual. And what's the practical application of this? Magnifying glass. Got it? Done with lens. Right? Only 20 minutes.